Hi, my name is Samodha Fernando. I'm an assistant professor in the animal science department at the University of Nebraska. By training, I'm a microbial ecologist interested in studying the rumen microbiome. The rumen microbiome is a complex environment. It's one of the diverse microbial communities, and there's a microbial food chain within the rumen that actually helps digestion of the feed. So the ruminants can survive on low quality forages because of this rumen microbial community. These microbes provide the animal with nutrients that are available to the monogastric animal. So this complex interaction within the rumen ecosystem actually helps these microbes thrive and actually provide about 70% of the energy that the animal needs from this microbial digestion. So if you look at the rumen microbial ecosystem, so the substrates of one organism would be the end products of one organism would be a substrate for another organism. What that means is these microbes actually have a lot of interactions between them, so that makes the rumen be a more efficient ecosystem. So how does methane being produced in the rumen, and how does these microbial fermentations affect methanogenesis? So if you look at this different pathways within the rumen, you see that when we produce acetate or butyrate, we actually produce more hydrogen and CO2, and these are substrate for a group of microbes known as methanogens that can actually use that hydrogen and CO2 to produce methane. Whereas if you produce propionate, as you can see here, you are actually utilizing hydrogen, therefore you are reducing the amount of substrates that's available for the methanogens to use as a substrate for methanogenesis. So by producing more propionate, we can actually show that there is a lot of more hydrogen being used, therefore there is less methane being produced. So what's the role of the methanogens in the rumen? So if you look at this figure, you can see in the rumen, which is anaerobic, glycolysis is key for metabolism. So during glycolysis, there is NAD that's been reduced to NADH. So you have to recycle this NADH back to NAD for methanogenesis to move forward. So what these methanogens actually do is reduce the partial pressure of hydrogen inside the rumen, so that this NADH, or the hydrogenases that convert this NADH back to NAD, can efficiently work. So when you have in the presence of methanogenesis, by methanogens, you are actually reducing the partial pressure and recycling some of your NADH back to NAD, so glycolysis can go forward. In the absence of methanogens, you have to use some of the pyruvate that could go into VFA for methanogenesis, VFA that could for VFA production. So what happens is you're using some of the pyruvate to produce methanol or lactate instead of using it for VFA production. So you're actually wasting some of the pyruvate that could go into VFA production. So in the absence of methanogenesis, actually, or the methanogens, you are actually being less efficient in compared to when you have methanogens. So ultimately, if you want to really control this rumen microbial population to reduce methanogenesis, we have to look at what are the alternative methods of using this different hydrogen or CO2 being produced within the rumen. One alternative is acetogenesis, where there's a group of microbes known as acetogens that actually use the CO2 and hydrogen to produce acetate, which is beneficial, but the problem is these acetogens cannot compete on growth rates with the methanogens. The other option is sulfate or nitrate reducers. In case of sulfate reducers, they produce hydrogen sulfide. Hydrogen sulfide is toxic to the animal, so therefore it's not a viable strategy long term either. The other option is nitrate reducers, but nitrate reducers actually reduce nitrate to nitrite and ammonia, and nitrite accumulation can lead to nitrate toxicity inside the animal. So a good viable strategy would be to try to see if we can increase propionate production inside the rumen to increase animal performance and decrease methanogenesis.